Chapter 6.1, Area of a region between curves. Finding the area of a region between two curves using integration. All right, so we've looked at the area underneath one curve. Today we're going to look at the area between two curves. All right, and it's really a very simple process. Think of it as if you're looking for the area between two curves, really you want to find the whole area underneath the upper curve, and you're going to subtract off the area underneath the lower curve. So really what we're doing is we're going to do the area between two curves is we're going to integrate just the subtraction of those two functions. All right? We're going to find the area of the upper minus the area of the lower. Really, it simplifies to the area of the subtraction. All right, so let's find the area bounded by the graphs y equals x squared plus 2, y equals negative x, between the values of x equals 0 and x equals 1. So we'll start by sketching a graph of this. So x squared plus 2, right up here, and y equals negative x, right through here. So we're looking for the area right here. And even though this part is below, we're still going to subtract, because we'll be subtracting a negative number, and it'll all work out okay. So we're looking for the area between these two curves right in here. We're going to sum up our infinite rectangles. We do that with integration. So our area equals the integration from 0 to 1 of the top curve minus the bottom curve. And so then our integration, our integrand, simplifies to x squared plus x plus 2, and we'll integrate that. So x squared becomes 1/3 x cubed plus 1/2 x squared plus 2x from 0 to 1. We'll stick in 1, we get 1/3 plus 1/2 plus 2. We'll stick in 0, we get 0. Subtract the 2, we get 2. Half is 3/6. 1/3 is 2/6. 3 and 2 is 2 and 5/6. That's as simple as it is. You take the top minus the bottom and integrate. Okay? Looking at another example. Find the region, the area of the region bounded by the graphs of 2 minus x and x. So again, we'll sketch these. 2 minus x squared, it's an inverted parabola, and y equals x comes through right through there. Here, notice they didn't give us any left or right boundaries. That's because the graphs intersect. And we're just looking for this area and here. We'll sum up our infinite rectangles from there to there. So first thing, you're going to need to find the intersections. Where does x equal 2 minus x squared? A couple ways you can do it. I'm going to do this by hand. So 0, or let's get everything onto the left side. X squared plus x minus 2 equals 0. So we'll factor that. We got x plus 2, x minus 1. The intersections are at x equals negative 2 and x equals 1. So when x equals negative 2 and x equals 1, and then the y value will be 1, x value will be negative 2. My graph isn't a very good graph. It doesn't show it, but the math supports that that's the way it should be. So we'll find the area. We'll do the integrand from negative 2 to 1, okay, of the top minus the bottom. The top function is 2 minus x squared. The bottom function is x with respect to x. One thing I want you to start noticing is these rectangles we're drawing. All right? They're all perpendicular to the x-axis. All of these rectangles have a finite or infinitesimal length, that's width, that's perpendicular to the x-axis. That is why we're integrating with respect to x. Whenever we integrate, we're going to see these infinite rectangles, and they're standing up on the x-axis. So that's integration with respect to x. So let's do this. Our area will integrate. No need to put it in standard form, though if you want to, feel free. It'll be 2x minus 1/3 x cubed minus 1/2 x squared from -2 to 1. All right, we'll stick in 1. We get 2 minus 1/3 minus 1/2. And then we'll subtract what we get when we stick in -2. -4 minus -2 cubed is -8. So minus a -8/3. If we stick in -2, -2 squared is +4. So 4/2 is 2. All right? We can kind of simplify this. So we've got 2 minus 1/3 minus 1/2 plus 4 minus 8/3 plus 2. Simplify 2 and 2 is 4. And 4 is 8. -8/3 minus 1/3 is -9/3, which is -3 minus 1/2. So 8 minus 3 is 5, minus 1/2 is 4.5. Right? The sine and cosine curves intersect infinitely many times. You guys know what the sine curve looks like. You know what the cosine curve looks like. They intersect, and this pattern repeats itself infinitely many times. What is the area of each of these? Right? So first we need to figure out where they cross. And if you remember your common angles, you know that sine and cosine are the same. When the angle is pi/4, and then that would give us the square root of 2/2. Right, same thing here. The next time they intersect is in the third quadrant, which would be 5pi/4. And then that would be negative square root of 2/2. We're going to set this one up and do it on the calculator. Now in this region, our rectangles, they stack across the x-axis. We're going to be with respect to x. Our top function is the sine function. Our bottom function is the cosine function with respect to x. And since we're with respect to x, our limits need to be in terms of x. So we're going to throw our limits in as pi/4 to 5pi/4. So there's our setup. Let's use the calculator to do an integration. First thing, always when doing calculus with trig, make sure you are in the correct mode. And we are at radians. All right, so we'll integrate it. Math 9. The lower limit is pi/4. The upper limit is 5pi/4. And it's sine of x minus cosine of x with respect to x. If you want to try it by hand and check first, that's a good thing. But it works out to be 2.828. All right? So basically what's happening here is we're doing these rectangles. All right? We're using a known formula from pre-calculus, width times height. All right? And because we're doing these vertical rectangles, our width of each of these, we want it to be really, really small. That's where the delta x comes in. Okay, the delta x, we want delta x to approach 0, so we get really, really small rectangles and do a lot of them. The height is actually the value of the function, or the difference of the functions. And when we integrate that, these infinitely many rectangles of infinitesimal width, we end up getting this, the integrand. This represents the height, and this delta x, that ends up representing the width. And so that's what we're doing when we're doing this integration. Remember, it's a limiting process where we have a limit of infinite rectangles of infinitesimal width. So in conclusion, when we find the area of curves, how do we do it? Well, we're going to integrate. We're going to integrate from the left to the right of the top function with respect to x minus the bottom function, in terms of x, all with respect to x. Now, if you want to, and it makes more sense, there are times when you can go sideways with respect to y. If you do it sideways with respect to y, we'll integrate from the lower limit, which in this case will be down, to the upper limit, up. And here we're going to go right function in terms of y minus left function, because we want the upper numbers to be first, with respect to y.